Problem 10 begins by asking us to sketch a graph where y quintuples when x doubles. So I've got an attempt at a horizontal axis here. It's going downhill, but and a y-axis here. We want x values to double, so we'll choose a large x value to start, and we'll cut that in half, and we'll cut that in half, and we'll cut that in half. So we have a series of x values, each one double the preceding. Double this, you get this. Double this, you get this. Double this, you get this. Now there's some flaws. This point should have actually been a little further over, or this one a little further over that way. But again, we're trying to be as accurate as possible. We're not going to worry too much. Okay, so we want y values to quintuple. Quintuple means increase by a factor of 5. So maybe I'll write that down. This means increase by factor 5. Now, as before, we're going to go in reverse. We're going to start with a large value of y, and we're going to probably pair that value with this value of x. And then we're going to find a value that's 1/5 of this, and then a value that's 1/5 of that, and then, if possible, a value that's 1/5 of that. Although I don't think we're going to be able to go to that that last step. Okay, so let's see. Let's just estimate. Let's see. Half would be about here, and half of that would be about here, and 1/5 would be a little less than this because this is 1/4. So I'd say that this is about 1/5. Yeah, I kind of overestimated it, but again, we'll not worry too much about that. Then 1/5 of this, I'm going to say, is down about here. So we could go 1/5 of that. It would be really close to the axis. Maybe we could distinguish it from the axis. So let's say we have a point way down here near the axis, and then a point here, so that as x doubles from here to here, y increases from this value to this value, factor of 5. Another factor of 5 to come out to this point, so that would put us about here. And then another factor of 5 here. Okay, I don't know how well I did, but that comes reasonably close to what we're after. And as usual, we know that if we keep cutting the x values in half, we're going to have to keep cutting y values by a factor of 5, so that the x values are going to approach 0 and the y values are going to approach 0. So that it makes sense to include the origin as a point on the graph, or to extend the graph to include the origin. So we draw what we hope is a smooth curve through these points, and now we have the graph, the quintupling graph. Okay. Okay, now we're to pick 4 points on the curve, none of which are too close to any of the others, and none of which coincide with any of the points that we originally drew, that we originally used to sketch the graph. So here are 4 points. And now we're supposed to pick one of the points and pick coordinates for that point. So I'm going to pick my 3rd point here, and I'm going to say, okay, the coordinates of this point are 5, 7, which means now, of course, that 7 is going to have to fall here on the x-axis, and 5 is going to fall here on the y-axis. Then we're going to scale the entire graph. Now I'm going to do that off camera because everybody knows how that would be. We can figure out where 1 would be if this is going to be 7, and where 1 would be if this is going to be 5, and then we mark the graph off. Okay, I probably could have done better, but here we have 1 through 7, and of course then we probably want to go ahead and do 8, 9, 10, 11, So here would be 10. And now we want to estimate the coordinates of our other points. I've done that off camera. Once we have the scale, it's easy to project down and over. And these are my estimates. Okay, the next thing we want to do is sketch a tangent line to each point. Now I'm actually going to use a straight edge. You can do this by just by eye if you wish. But you know, right there would be a pretty good tangent line at this point. So I'm going to raise it up just a little. Okay, I'm going to say that's my tangent line at this point. Not sure how well I did, but okay. I'll draw the others freehand. This one out here, this one out here. I kind of didn't exactly fudge because it wasn't intentional, but yeah, I've got one here. So there are 4 tangent lines. Now we're supposed to find the slope of each tangent line as best we can with our scaling. All this is going to be pretty approximate, but we're going to use the same procedures we would use if we had a really accurate graph. Okay, well, the slope of this tangent line, let's just pick 2 points on the tangent line, and I'll draw a right triangle with sides parallel to the x and to the y axis. And then what are the I could estimate the coordinates of this point and this point. Or I could just say, well, this is how far this is, and that is 2.7. And that's, of course, the run. And then how much does the graph go up? It goes up this much, and that appears to be 3.8. So the slope of this tangent line would be rise divided by run, 3.8 divided by 2.7. I'm going to go off camera and do a little more. You'll understand when you see it. Okay, completing this. Between 2 points here, I found a rise of 3.7, run of 2. Down here, rise of 2, run of 2.2. Down here, the rise was about 1, the run was about 2, so the slope was 0.5. And we get the 4 slopes corresponding to these points. We now tally the x-coordinates of the points that we chose and the slopes, the y', well, we'll talk about y', the slopes that we calculated at each of the respective points. And we're going to call the slope, we can't call it y because we're calling this y. So we're going to call this y'. X is still x, and now we've got y'. And the values of the slope y' go from 0.5 to 1.9, so we'll mark that axis off with a scale of 2 here, and a scale of 10 on the x-axis because the greatest x value is 10.2. Now there was an error I made earlier. I had this point labeled 5, 7, and it's 7, 5, at least the way I plotted it. I think I said 5, 7, and then proceeded to put 7 here and 5 here. And that was completely wrong, and I apologize if that threw you off. But changing that to 7, 5, now our graph is consistent. And of course, the x-coordinate here corresponding to this point is now 7 instead of 5. So, plotting these points on this scale and just subdividing each scale as appropriate, we get a set of points that look like this. And we can't tell for sure because everything is an estimate, but this looks almost like a straight line through the origin, maybe even. We don't know, but we can speculate on the possibility that this might actually indicate a straight line through the origin. Now, the slopes of tangent lines in the progression of the slopes of tangent lines turns out to be something that's extremely important because, of course, when we interpret trapezoids, and these tangent lines are just close to the slopes of small trapezoids, thin trapezoids near these points. Slopes of trapezoids have interpretations, and the values along the x and the y axis have interpretations. And sometimes, quite often in fact, matter of fact usually, the slope has a very significant interpretation. And this slope graph, the graph of the slopes, is an extremely important graph and has some very subtle and interesting relationships with the original graph that we won't go into, but that you'll see by the time you get to a calculus course. Okay, now just a little extra. We've already seen, and we should know, how to get the formula for the function of the quintupling graph. It's a y equals ax to the p, where in this case 2 to the p equals 5. That tells us that p is approximately 2.3. You can get that using logarithms, or you get that using trial and error if you don't know about logarithms. Now, when x equals 7, y equals 5, so 5 equals a times 7 to the 2.3. Substituting the x and y values, we solve that. We get a approximately equal to 0.057, so that our function is now y equals 0.057x to the 2.3. If we evaluate this function for these x values, we get y values 0.25, and of course these x values correspond to the points that we chose for which we estimated the coordinates. We get the values you see here, 0.25, 1.465, 11.9. That compares, well, the 0.25 compares with the 0.6. There's a significant amount of difference there, but and the 1.46 compares with 2.7. That's not great. And the 11.9 would compare with the 9.6. These values don't match up very well. And this just means that when I constructed the quintupling graph, I don't appear to have done a very good job of it. But of course, this is constructed by hand, a carefully constructed quintupling graph. If you go through this whole exercise, and of course on a test, at this point I'm just grading you on your ability to follow these instructions and do these constructions, and not expecting miracles of accuracy any more than I performed miracles of accuracy when I did this. Okay, the value, of course, for x equals 7 agrees perfectly well. The value for x equals 4.1 is quite a bit low. It should be 2.7, it's 1.46. The value at 10.2 is much higher here than it is here. So this value is lower than this one. This value is higher than this one, which means had I constructed a good quintupling graph, it would have dipped down more here and gone up steeper here. Now I started to draw a slight correction, and when I got to this point where I was going to graph 4.1, 1.46, which would be about 1.5, I found that that was really close to this point, and I realized that I wrote this point down as 2.7, and it should have been 1.7. Making that correction, this value is pretty close to this value, and this value is not all that much higher than the 9.6 that we get here. And this point would just be a little bit lower, and this point would be somewhat lower, but it's everything's really close to the axis there, which means that our accurate curve would probably be a little lower here, meet up with the graph that we drew here, and be just a little higher here. So I didn't do as badly as it appeared maybe that I had. Now, through the magic of calculus, which I don't expect that you know, I know that the graph, or the function that governs y prime, the slopes of this graph, is about 0.13x to the 1.3, and that's very easy. It's a very easy rule of calculus that allows you to get this from here, but I'm not going to talk about that. So through the magic of calculus, we know this is the y prime value, so we can evaluate y prime at all these values of x. So if we compare the y prime values calculated here with the values that we have here, they're all pretty close except for this last one, which is off just a little more. So we see that it's possible to construct an unscaled quintupling graph do all this, get all these estimates, and come out reasonably close to the ideal results.